Good afternoon, good evening, and to some places, good morning. Welcome to this webinar by ICORR Institute of Corrosion Midlands branch. And My name is Praful Sharma. I'm the chair of Midlands branch, and happy to have with us Dr. Ali Oskuie, uh, who will be talking about reliability models in asset integrity. It's an interesting topic. There's a lot of interest, and we're expecting a lot of attendees for these webinars from across the various geographies. So just to introduce Ali, Ali is currently an asset integrity engineer with Worley, based in London and UK. But he've got PhD in corrosion engineering and overall more than 13 years of experience in this space of asset integrity. So we're keen to hear his enlighten us with the topic. So over to you, Ali.
Thank you very much, Praful, for the introduction. I hope my sound is good, so I can start sharing the screen. Thank you, everyone, for joining. So I hope you can see my screen now. Yeah.
Yeah.
Okay. So I start the presentation. So our presentation today is with regards to the application of reliability models in asset integrity. Before joining this session, I told Praful that this actually presentation is based on my previous experiences as asset integrity engineer, corrosion engineer, and hands-on experience in the field, and the statistical distribution, statistical models application in our field, because usually as corrosion and materials engineers, we do not expose to these kind of subjects, but I try to explain the aspects of a statistical analysis that are helpful for all asset integrity engineers and corrosion engineers. So the contents of today's presentation, I try to give a kind of introduction to reliability engineering and how it is related to asset integrity management. I will discuss the statistical models and their applications. Also, I introduced a very interesting topic with regards to frequentist versus Bayesian statistical analysis, which is very important with regards to our knowledge that we gain through inspections, and it's basically one of the fundamentals of API 581, API 580 and 581 for risk assessment. I introduced that as a very broad topic, but I try to give you as much as I can here, and we talk about key takeaways from this session. And at the end, we have a Q&A that will be listening to you in order to answer any questions you might have. So with regards to reliability engineering, reliability engineering is a discipline that quantifies the probability that an asset will perform its required function. We have three parameters that should be satisfied, and reliability engineering basically takes care of it and quantifies the variables that are within these three, that are actually defined within these three parameters. So our three notions. One is that we have to make sure that the asset does not fail. The other one is it satisfies certain specified operating and environmental conditions, for example, maximum local working pressure, the maximum temperature, etc. So it should satisfy those kind of functions, and it should provide service for a certain period of time. So if you look at this triangle, these are also common in asset integrity management. So when we are dealing with asset integrity management, working as asset integrity engineer, we have the technical integrity, which is defined as for an asset to be fit for service. We have operational integrity, which is defined as the capability of the asset to operate at design capacity. And what is important, most important, is that the asset should have a certain remaining life. As this remaining life is one of the aspects that is very much taken care of by reliability engineering. So, in summary, AIM ensures integrity, and reliability engineering quantifies how long that integrity can be relied upon. So, reliability engineering basically is a foundation to asset integrity, and I explain how we can use the models and parameters in order to ensure that asset integrity is achieved. So now I'm going to give you an introduction about the probabilistic models and random variables, which are the very basics of a statistical analysis. I want to make a distinction between deterministic versus probabilistic models. So most of you are, I'm sure, aware of standards in the field. So if you see, for example, APR 581, we have an extensive section which provides theoretical models based on chemio-physical attributes of a corrosion mechanism, for example, CO2 corrosion pressure, the amount of sour gas. So these factors are actually plugged into a formula in order to find out, for example, corrosion rate for a certain type of damage mechanism. But this deterministic way of approach has got lots of limitation. And the main one is that we do not know all the contributing factors here. For example, for a complex system, there are lots of chances that theoretical models might fail. So this limitation has made us to actually have a kind of look at the statistical approach or probabilistic approach in order to basically include all those factors that we cannot consider while we are doing our assessment. And we have we have some variables that we can consider in order to use the statistical models for example, time to failure or maximum allowable stresses. So these variables can be approached via probabilistic models. I wrote a sentence or kind of a word from Laplace, who's I can say father of the statistical analysis. So it says probability theory is a measure of our ignorance. So basically, when we know something, we can use deterministic models. But when we don't know about something, we should have a kind of probabilistic approach. So that's why we need reliability engineering and probabilistic approach in our assessments. I brought some distribution models in order to give you a sense of what we are dealing with here. So one of two most famous distributions that we have are binomial distribution and Poisson distribution. So I'm sure you're aware of the the trial and errors that we do usually, for example, by tossing a coin. So these things can be modeled by binomial distribution, and basically this formula. So if I want to say, for example, probability that we have a certain number of, for example, heads or tails, depends on the probability to the power of the number that we are trying to the probability. For example, if we want to have heads, the probability of having heads or success event, if we can define it as success, to the number of trials multiplied by the 1 minus the probability of success, which is a failure, and to the power of the number of trials minus the number of successes we have. And another distribution which is also useful and is very useful in terms of corrosion is Poisson distribution. So it's very useful for events occurring randomly in time or space with a fixed rate. And this is the formula. So lambda is the rate of the failures, and K is the number of events or successes that we want to experience. So these two formulas just provides you with a kind of sense of how we're dealing with the probability here. And these are the distributions. For example, this one is for normal distribution. Sorry, this one is for binomial distribution and Poisson distribution. But please pay attention, these are discrete distributions. I also introduce continuous distribution in next slides. I brought an example of application of, for example, Poisson distribution calculation in corrosion. So imagine that we have inspected a high pressure pipe, and we find out that on average there are 2 pits per meter of pipe occurring during the service. So assuming the pitting intensity is constant, so this lambda is constant, and it is 2 pits per meter of pipe, what would be the probability of having less than 5 pits in 10 meters of pipe? So as you see here, if we put lambda as 2 pits per meter, and on average we expect to have 20 pits in 10 meters of pipe. and plugging them into the formula for Poisson distribution, we can find out that for more than 5 pits to exist in this length of pipe, this probability is very high, so 0.99. So this way, we can basically understand the possibility of observing pits during our inspections. So, and it's very helpful in order to plan for inspections afterwards. If it's very high, we should approach it as quickly as possible. If it's not, we can put it for later on. So these are the kind of application of discrete probabilistic models. Another important factor that we have in statistical analysis, which is related to the life cycle of asset. I'm sure that most of you have heard about it. It's a bathtub curve. So it is related to, for example, if you imagine that we have a vessel or we have a, for example, tube bundle, whatever, or any kind of electrical instrument, we expect to see during the life cycle of that equipment, a piece of equipment, we expect to see a decreasing rate of failure when we commission that equipment until we reach a constant rate, and then afterwards we have a kind of increasing rate. So it's very, and this kind of they call it bathtub curve because of its shape. So it's very useful in order to see at what stage of the life cycle we expect different kind of failure rates. So I'm sure that you've experienced it, for example, for cars, for electrical instruments, when there might be some kind of failures early in life of the asset. So it's called kind of burn-in failures. But after some time, the number of these failures should reduce because these failures are due to the fabrication issues. They are not relevant to corrosion or any problem. So these are due to construction fabrication issues. And after some time, the number of these failures reduces, and afterwards we actually enter a kind of constant rate phase of failure, and it's a random type of failure, and it can be caused by various type of issues that happens during the operation of a vessel or a tube bundle. And basically, this encompasses the longest part of the asset life cycle. And after that, we enter the wear out stage, which can caused by corrosion or by cracking mechanism or material degradations. So you can see an increasing rate afterwards. And it shows that if we have statistical models, we can predict, and basically these statistical models are built based on the data that we have for certain type of vessel or tube bundle or whatever equipment we are studying. We can plan for inspections and allocate assets like inspection campaigns or whatever we want to do in order to mitigate them. So this is very helpful if we can produce such kind of curves for our systems and equipment. Here I brought some examples of distributions that we usually use and the applications. Just let me just magnify this. For example, here we have these are the continuous distribution models. So if we have exponential distribution, which is very similar to the Poisson distribution. So we have lambda an exponential of minus lambda to t, which is t is the time. So just I skipped the details. I want to show you that, for example, this exponential distribution is useful for life distribution of complex non-repairable systems. For example, in case of tube bundles, you cannot usually repair it after some time, so you should replace it in case of tubes. Or, for example, life distribution in the burn-in phase. If I can compare it, for example, with Weibull distribution, which I get to in later slides. So Weibull distribution is a more complex distribution type. So cumulative distribution function is like this. As you see, based on the parameters of the distribution, we might have different shapes. If you remember the bathtub, so we had a kind of decreasing rate, constant rate, and increasing rate. So you see viable distribution is capable of modeling of all those three stages that we saw in the bathtub care. But for example, in case of exponential distribution, we have only kind of constant phase. So this way, you can different distribution functions, statistical distribution functions can be useful in order to model the life cycle of an asset. For example, in case of viable, you see the applications of corrosion resistant life distribution of many basic components. For example, one of the main application was actually this viable distribution has been introduced was to model the failures of landing gears in aviation industry for airplanes. And so just wanted to give you some examples of distribution. We have normal distribution, which I think we kind of most of you are familiar with that. So it's a very common distribution that is very applicable in statistical analysis. So here I try to because of the application of viable distribution, I chose this distribution to introduce to you how it works and actually how we can read the graphs here. So it's a statistical model which is actually developed during 1970s by a scientist mathematician called Weibull. He's a Swedish mathematician. And as you see, for example, in every graph of viable distribution, so it's a cumulative, this graph is a cumulative distribution function. So in the horizontal axis, we have the hours or number of cycles or whatever random variable that you have. And here we have unreliability or failure percentage of the component that you have. So we have time versus the probability of failure. And as you see, we have data points. So these data points are used in order to create or by means of regression, we produce a kind of graph that can be predict the probability of failure outside the ranges that we have data. So as you see, for example, if the time grows, the percentage of failure also grow. And this way we can predict, for example, if we set up a limit, for example, we say the acceptable probability of failure for us is 10%, 50%, we can determine what would be the remaining life or what's the actual failure life of our component. And based on the appetite or risk appetite of our company, we plan for example, replacement or any repairs. And also it's very useful to determine the warranty periods because, for example, the warranty period usually for example, electrical devices, they want to have the kind of time that less than 1% of the components are failed. So by using this kind of viable model, you can determine what would be the warranty periods that are useful for different components, for example, electrical components like lamps, et cetera, in order to actually not put the company in danger by accepting lots of liability. So for viable distributions, we have two parameters. One is called shape parameter. The other one is characteristic parameter. Characteristic life. Shape parameter is the slope of this curve, and one of the application of viable is that when you actually apply a graph on a set of data based on shape parameter, you can decide what is the failure mechanisms that you have. So when, for example, the slope changes, for example, from a lower slope to higher, so we can say the mechanism, for example, changes from thinning to cracking, because cracking is a very sharp increases the failure rate sharply. So by comparing the beta or shape parameter, you can distinguish between the failure mechanisms. And characteristic life is basically defined as the time that you have 63% of chance of failure, and it's shown on the graph by how up and down this graph actually moves. When it moves up, the characteristic life increases. When it goes down, the characteristic life decreases. Here, I wanted just to introduce that this graph is not enough by itself, because these graphs are based, as I said, there are regressions on a set of data, but we have a kind of uncertainty around those data points. So these uncertainty is defined by kind of calculation which we call confidence intervals. And these confidence intervals are very important in asset integrity management and, for example, risk assessments. And it shows itself in the techniques that we use, for example, for inspections. As you see in this graph, for example, here we have the 90% confidence bound. So similar to the previous case, we have a Weibull graph. This area shows the area that we expect that 90% of real data that we get during operational inspection would fall within that boundary. So if you decrease the confidence, then this area grows. If you increase the confidence, this area actually approaches this line. So for example, if you have 99%, it approaches this line because there is less chance of having an actual data outside that. And in this way, we can define the effectiveness, for example, of inspections. If we have we use more advanced techniques, or we have additional inspections, we can reduce the level of uncertainty around our data points, and we have more confidence in our predictions with regards to the models that we use. Another important kind of application of statistical analysis is when we are comparing the stress versus strength of one component. For example, if we have a vessel, imagine that we have a certain resistance or certain mechanical strength for the vessel, for the metal that we have for the vessel, and the level of stress is applied. And as I told you, usually these are not deterministic. So we have a distribution of a stress and a distribution of a strength based on the type of material that we use, the quality of the material. So statistical analysis helps us to understand whether by certain confidence level, we can say that at this stress distribution level, the material or the vessel can withstand or not. I just brought the example here. For example, here we have two distributions for stress and strength. As you see, usually strength should be the average value is higher. So this distribution here is a normal distribution. So what we do, you see, we have the average value of strength and an average value of stress. So it's 40,000 psi for strength and 30,000 psi for stress. And the standard deviations is 4,000 for strength and 3,000 for stress. So as you see, 4,000 is for here, and this is basically how blunt the graph is. So we want to have also a safety factor of 1.33. So we have to compare the averages, and this gives us this safety factor. In order to see what's the confidence that we can say, for example, this vessel with this metal strength can withstand this stress distribution, we should build the kind of joint distribution, which is produced by subtracting these two the stress distributions. And it's just, I don't want to get to the mathematical calculations. But for example, in this case, we can say that the reliability of getting a vessel which can withstand this stress level is 97%. And this is calculated based on the distribution of a stress versus strength. So this way we can predict what is the chance of getting a failure if we have such distributions. For example, in this case is 0.023. So it's very low, but sometimes it might be very high value depending on your thresholds that you can accept. Up to now, what I discussed was a kind of set of statistical models, which is very much applicable in industry and reliability engineering. It's called frequentist approach. In recent years, not in recent years, it's 20 years since RBI methodology developed, they tried to use another statistical approach, which I'm going to explain to you the difference. So in the frequentist view, which I showed here, as I said, for example, in case of tossing coin, if that coin is fair, we expect to see, if we run the trials for many times, we expect to see the probability of 0.5 of heads and 0.5 of tail. Maybe in 4 or 5 trials, we don't see this 0.45 number for probability, but when we try a lot of times, we get to this value, and we expect to get to this value. In other words, it seems that in frequentist point of view, we have a reality, and this reality actually shapes when we do our trials many times. In contrast to this view, we have the Bayesian view. So in Bayesian view, the reality shapes itself by the kind of findings that we get through, or the knowledge that we gain through doing inspection. So it's the reality actually develops with time. I will explain it further to you, just to give you a formula. So it's a mathematical formula, which is this sign represents the probability of an event given another event happens. For example, imagine that we want to know the probability of a failure given a defect of a certain size exists. So this is calculated by multiplying the probability of, so the prior knowledge that we have. Imagine that we know that, for example, a vessel or a tube fails with certain probability before we doing any inspections or doing any kind of test. So this is a priori knowledge that we have multiplied by the likelihood of failure, given that the probability of the defect size, given that the failure happens. This is called likelihood. So it's a kind of opposite of this probability that we're looking for. And in this way, and this probability of defect size is something that just we want to normalize this calculation. So just to make it simpler, this formula wants to say, in order to understand the probability of failure given a defect size, we should update our previous knowledge, which is PA or priori, multiplied by the power of our, for example, inspection methods, or the certainty of our application inspection methods, in order to update that priori knowledge, in order to form a posterior knowledge, which is the knowledge we gain through that inspections. I just passed this kind of approach is developed by Bayes, which is the gentleman on the right, and is developed by Laplace. Just to give you a kind of historical context. But let's see, what does it mean? So in the frequentist approach, imagine that we have a picture, and by every trial that we do, part of this picture actually becomes visible. But the picture itself is a short one. So when we just do trials, we try to get to that kind of final picture. But in the Bayesian approach, this picture is vague, and as much as we do inspections and as much as we do trials, this picture becomes sharp. So in other words, by doing inspections, by getting information, we can create a better kind of view. And it's got lots of roots in philosophy. So we have kind of experimentalists like Hume, and we have also Descartes, who thought that we can gain knowledge through just thinking, so it can be separate from experience. And we have Immanuel Kant, who says that this is something in between. So we need priori knowledge, experience, in order to mingle them together, in order to get a posterior knowledge, and basically get a better understanding about our surroundings. And if you see, it exactly is in the cycle as very familiar in asset integrity management textbooks. So we have this is called cycle of excellence usually. So we have so imagine that we want to plan for the integrity of an asset. First of all, we have to have a kind of idea about the condition of the asset. And usually these ideas are formed by statistical models we gain from historical data books, the previous failures. So for example, we build a viable model of the failure rates, and we can predict based on the previous experiences, what would be the probability of failure? So we hypothesize the failure rates. We do the test, and by testing, I mean doing inspection. We gather information. And then we update that knowledge based on the formula that I said. So it's a Bayesian formula. We can update that knowledge. And based on this updated knowledge, we can plan again because it's no longer that hypothesized kind of probability. It's a new probability based on the evidence that we gain. And by this cycle, we can gain a better knowledge about the asset. And in future, we can plan better. That's why it's this type of approach to statistical analysis has gained lots of attention and is used in the API 580 and 581 in risk-based assessment. And if you check, for example, in the part which are related to thinning, you can see it was not mentioned explicitly in the it's not, the details are not provided, but basically it's the statistical approach which is used in those studies. I'm a little bit conscious of time. I passed this one. Just I want to show you what effects have here, for example, how we can use this idea in order to determine the inspection effectiveness. So, for example, in this case, we have for example, if we imagine that prior to doing the inspection, we do not have any idea about the defect size in a vessel or on a piece of metal. So it's a random probability. It is equal through different defect size. And here it is the type or the type of inspections that we have or the number of inspections we have. If the type of inspection that we do, for example, a very advanced PAUT, you see, we can determine the likelihood of defects around 5 minutes is very good. So it's very sharp. But when we use a less advanced technique, yeah, we get the peak at 5, but it's very blunt. So when we combine this prior probability with this technique using the Bayesian approach, the posterior probability that we get through better advanced techniques gives us a sharper view of the actual condition. So this way, we can define the inspection effectiveness, and basically Bayesian approach can define the applicability and the usefulness of different inspection techniques. So it can assign likelihoods to the number of inspections that we do. That's what is used in API as well. So just to finish this presentation, I want to give you kind of takeaways. So in asset integrity, uncertainty is unavoidable, and probability statistics provide a disciplined way to quantify that. I introduced the viable distribution as a kind of very useful distribution in order to determine the remaining life, and which is very useful in asset integrity management applications to determine the remaining life of tube bundles. Also, we actually introduced the Bayesian statistics and how is it different? It is different from frequentist approach and is very useful tool in order to gain knowledge and to be used in risk-based assessment and planning. We have also get an idea about the inspection effectiveness, how it can be quantified using Bayesian approach. And if you want to know more about the Bayesian approach, I put a link here. It's very interesting clip on the YouTube that you can use and enjoy and learn more about it. Thank you very much for your attention. I'm available for any Q&A afterwards.
Thank you, Ali. I learned a lot in a very short period of time. Not sure I understood everything, but
Okay.
you're always a phone call away if I have questions. So to the audience, so Ali, if you can unshare it, and then we'll ask the audience if you want to post your questions, please put your questions in the Q&A tab. We already see some questions already coming in, so please feel free to write your questions in there. So, so Ali, I'll read out the questions, pick and choose, and then you can answer that. So the first question
Okay.
coming out is, why is the characteristics life 60% chance of failure?
Yeah, it's based on the formula of viable distribution. If I can I share it just to show
Yeah,
it?
sure.
So if we go back to, I have the formula here. Okay, let me magnify. So here, the CDF is lambda. Sorry, this one is the variable distribution here. So here it's shown by the naming is different. So alpha is the characteristic life here. So if you put the timing equal to alpha, then the probability that you get is 63 with a constant beta. So it just shows you. So when you put the t equal to eta, the cumulative probability would be 63%. So that's how it's defined. I hope it answers the question.
Thank you. Thank you, Ali. Another question came in. When would you suggest using Bayesian statistics rather than an a priori method? Do you need some failure data to do this, or can you help put limits on failure rates even without evidence of failure?
So there are two different approaches as far as I know. So frequent test is usually used when you have a kind of knowledge about the distribution. Frequent test approach is the best case. For example, you know that your distribution, your data actually matches the normal distribution. So frequentist approach is the best way because you know about the type of distribution and you just need to apply that distribution model to your data and get all the information that you want, like the average, or by setting, by determining the standard deviations, what is the chance of getting actual data at certain limits. But Bayesian approach is different. As I said, Bayesian approach is a developing method. That is the best way is the best approach when we are dealing with lots of unknowns and we want to update our data. So the distribution itself, the probability itself, if you remember the trials that we have in the case of tossing coins, as I said, the P, which is the probability for a fair coin, is 0.5. It's constant. So you don't have any uncertainty about that. But in case of Bayesian, in the Bayesian approach, you can also put a doubt on this 0.5 probability, and you can build that through the experiments or the inspections that you do. So in that sense, it's a more, applicable tool to improve the knowledge about the assets. So that's why the authors of API 581, they use that approach instead of using frequentist approach. I hope it answers the question. If you have any more question, I can
So, audience, please feel
elaborate on
free to
it.
write your questions in the Q&A tab. So, Ali, I have a question here. You talked about RBI API 581. Recently, there has been a discussion about the deterministic approaches of our API 581. Are they still relevant? Can we move to the more advanced approaches, which is statistical distribution-based approach and reliability models-based approaches? Um, so, being a practitioner in the industry, are you observing risk reliability models being applied to risk-based analysis in some ways?
Uh, so as I said, first of all, with regards to deterministic versus probabilistic, so API 581 provided the deterministic corrosion rates, for example, as a starting point. So sometimes, for example, imagine that you have a site or vessel which just put into service. So you don't have any data. So you should have a starting point, as I said, a priori to update that. So that deterministic formula serves as a starting point. Afterwards, when you gain knowledge through inspections, you can update that priori based on the actual experience and get to a more actual or more realistic kind of distribution function. This is the first part of the question. With regards to the application of probabilistic approach, or as I said, the best example is API 581, I can say. We have also other textbooks like the ORIDA handbook, which is used in reliability engineering or reliability centered maintenance. So this handbook basically is based on historical data. For example, we have a compressor, we have different parts, And for each part, for every part in the boundary of a compressor, they gathered all the historical data from main companies that are active in the field, for example, Shell, DNV, etc. So they put all the data and provided some kind of distribution models for the failures of each and every part of the compressor. This is another application that we have, and based on those distribution, you can predict the failures or the inspection or the maintenance cycles of your component.
Right. Thanks, Ali. I think we're getting some more questions. Not sure whether this is the right slide or anything, but any recommendations for books, reading material for reliability models?
Yeah, I have. So there is a very good book. I have it on my desktop. Let me just, in order to, if I can share this screen. See if I. So yeah, I can share it in the chat if I have.
Yeah, please
Oh,
feel free to share it in the chat.
okay. Yeah, it's a very useful book. It provides examples, etc. So it's called Reliability Engineering and Risk Analysis. Let me see if I can find the chat.
Yeah, you
Yeah, I
can
can.
post it.
Fortunately, I can't see the chat of this.
Or we can send it by email
Oh
to
yeah, but I read the text, name of the book. So it's Reliability Engineering and Risk Analysis, a practical guide. It's written by Mohammad Modares, and there is another book called the Certified Reliability Engineer Handbook, which is very useful because it provides a kind of overall overview understanding. It's very simplified, basically. And so the Certified Reliability Engineer Handbook is also another one, which I suggest.
got it. So another question which is coming in is, given these Bayesian methods, can you provide failure rates for processes with less data? Can it be used to reduce the number of
Yeah,
trials,
yeah.
amount of testing required for new processes or equipment?
Okay. So first of all, when we have less failure data, we should first of all distinguish between the approach and the distribution model. So for Bayesian approach, as I showed to you, we need a priori or a initial starting point distribution. So when we have less data, the best distribution model that we can use is viable. Is viable one of the application is that when you have very few data, it can produce a probability function. Bayesian Bayesian approach application is how to update the data based on inspection. So it's not relevant to the number of data points. So I want to make this distinction. When you have a few data points, viable distribution is a good way to build that priori or initial probability distribution. And when you do inspections, then you can develop that priori probability based on few data in order to get to actual probability distribution based on your actual circumstances, actual operation conditions. So there is a distinction. But when you have few data, I think viable distribution is the best.
Got it. Okay. And so what brings me to my notice, Ali, is obviously reliability engineering is a very well established field, but reliability centered maintenance is also gaining attention. However, we see the corrosion engineering is not necessarily integrated with reliability engineering. So, what is your take on this two different topics? Are you seeing the two domains being merging?
As a corrosion engineer myself, I think we use, maybe unknowingly, we use these kind of methods and these kind of techniques without paying attention. In every time for example, we calculate the corrosion rate based on inspection data, we are unknowingly using, for example, normal distribution. We calculate the averages, the standard deviations to have the confidence levels, etc. But what I see as in corrosion engineering, what I think is important is to not to get very much involved in reliability engineering topics, but to at least understand what are their limits and what are the application of each approach. For example, what's the application of frequentist approach, like distribution, as I said, to be familiar with for example, the notions like or the the um, notions that we have, like, for example, confidence levels. When we say, for example, what's the confidence level of this inspection methodology, what we mean by that. So I think as a corrosion engineer, it's good to have a certain level of knowledge of statistical approach to know the limits. And it opens up lots of, doors to a corrosion engineer in future, in future career of corrosion engineers, in order to work on, and for example, how to work with big data. When we have a big set of data, how we can actually extract information from those set of data. So in that respect, I think statistical analysis and understanding that is useful for corrosion engineers.
Got it. Thanks, Ali. I
No
think you
worries.
have paused your screen sharing, but if you could stop it, then we can answer more questions as well.
Oh, okay, I stopped that.
Um,
Sorry.
um, are there any statistics packages, preferably free, that I can use to access Bayesian statistics? That's one of the questions.
Uh,
Excel?
no, Excel is one. We have also R software. I think R software is also one of the free software. It's very, very useful. You can also, if you know coding, Python has got lots of good libraries for statistical analysis. But R software is free and also is very powerful. So usually statisticians use our software, and there are other licensed softwares as well in the market that you can use.
You need ArcSoft,
No,
ARC,
no, no, no. R. It's called R. Just letter R.
RSoft. All right.
Yeah,
Okay.
yeah.
RSoft. Okay. Got it. Okay.
I write it in the chat.
So
I just have access to the chat, so I write the name of the textbooks as well right now. Okay,
got it.
go
Thank
on.
you. So I think now there are no. I think you have answered all the questions. I think it was a very informative webinar. Thank you, Ali, and
Welcome.
a very good topic for our practitioners of corrosion engineering.
I hope it
So
is useful. Yeah,
thank you. Yeah. So to the audience, thank you for joining in, for tuning in today. So we are about to wrap up our webinar. And thank you to our speaker, Ali Oskuie, to elaborate on this topic. So at ICORR Midlands, we periodically, regularly organize these webinars, informative webinars on various topics. So please follow our LinkedIn pages. On LinkedIn, we have an ICORR Midlands page. So you can follow that for updates. And also feel free to reach out to us. For the attendees who would like to get CPD certificates, please email us at midlandschair@icorr.org. So you can email that requesting your name and specifics when you attended it, and we'll provide the CPD certificates as well. So with that, we wrap up this webinar. Thank you everyone for joining, and have a great day.
thank you.
Thank you. Thank you, Ali. Bye for now.